Bismillah ar-Rahman ar-Rahim. Function g is from R to R. Function g satisfies this functional identity. For every x in R, x² plus x is equal to 3g of x minus 5d of beta x plus 2g of 𝛽²x. Beta is a constant in the open interval between 0 and 1. Function g is continuous at x equals 0. G of 0 is equal to 1. Inspired by this x² plus x, let's consider a function f of x equal to c1x² plus c2x. What should be the constants c1 and c2 so that function f satisfies the same functional identity? We need 3f of x minus 5f of beta x plus 2f of 𝛽²x to be equal to x² plus x. Using this for f of x, equating the coefficients of x on both sides and x² on both sides, we get this equation for c1. So c1 is 1 over 2 beta to the power 4 minus 5 𝛽² plus 3. We also get this equation for c2, which is equal to 1 over 2 𝛽² minus 5 beta plus 3. Function f with this c1 and that c2 satisfies this condition that is also satisfied by function g. Let h of x be the difference g of x minus f of x. If we prove that h of x is equal to a constant, then the solution to this problem is this function f of x plus some constant. The constant is equal to 1 if we use this condition. These three terms are equal to x² plus x. Those three terms are equal to x² minus x. The difference is equal to 0. The left-hand side can be written in terms of function h. 3g of x minus 3f of x, that's 3h of x, minus 5g of beta x minus 5f of beta x, that's minus 5h of beta x. The last term is 2h of 𝛽²x. This is equal to 0. Split this term into minus 3h beta of x minus 2h beta of x. We get 3 between brackets h of x minus h beta of x minus 2 between brackets h beta of x minus h 𝛽² of x. If we define function h tilde of x to be equal to h of x minus h beta of x, the condition that we have here can be rewritten as 3 h tilde of x minus 2 h tilde of beta x. H tilde of x is equal to 2 over 3 times h tilde of beta x. This is true for every real x. We can replace x on the left and right hand sides by beta x. We get that h tilde of beta x is equal to 2 over 3 h tilde of beta times beta x, that's 𝛽²x. This means that h tilde of x is 2 over 3 times 2 over 3 times h tilde of 𝛽²x. We can keep doing this. If for some positive integer j, h tilde of x is 2 over 3 to the power j, h tilde of beta to the j times x, we can replace x on both sides by beta x to get that h tilde of beta x is equal to 2 over 3 to the power j, h tilde of beta to the j times beta x, that's beta to the j plus 1 times x. H tilde of x is equal to 2 over 3 times h tilde of beta x. H tilde of x is 2 over 3 to the power j plus 1 h tilde of beta to the j plus 1 times x. This relation is true for j equal to 1. If it is true for j, it is true for j plus 1. This means that for every positive integer n, h tilde of x is equal to 2 over 3 to the power n times h tilde of beta to the power n times x. We can take the limit of both sides as n tends to infinity. The left-hand side is h tilde of x. The limit as n tends to infinity of 2/3 to the power n is equal to 0. What about the function h tilde? H tilde is h of x minus h of beta x, and h of x is g of x minus f of x. It is given that this function is continuous at 0, and function f is also continuous at 0. H and h tilde are both continuous at x equals 0. For every positive epsilon, there exists positive delta, such that for every x satisfying that the absolute value of x is less than delta, we have the absolute value of h tilde of x minus h tilde of 0 upper bounded by epsilon. Fix any non-zero x. Let n be the ceiling of len delta over the absolute value of x divided by len beta. If small n is greater than big N, then small n is greater than this quantity without the ceiling, because beta is in the open interval between 0 and 1. If we multiply both sides of this inequality by len beta, the inequality is reversed. We get that n len beta is strictly less than len delta over the absolute value of x. Beta to the n is strictly less than delta over the absolute value of x. Then the absolute value of beta to the n times x, this is less than delta. Because of the continuity of function h tilde of x at the origin, And since this inequality is satisfied, then the absolute value of h tilde of beta to the power n times x minus h tilde of 0 is less than epsilon. For every epsilon greater than 0, there is a big N such that for every small n greater than big N, this absolute value is less than epsilon. This statement here is equivalent to saying that the limit as n tends to infinity of h tilde of beta to the nx is h tilde of 0. Let's go back here. When we take the limit as n tends to infinity, the left-hand side is h tilde of x. This part tends to 0 as n tends to infinity. H tilde of beta to the n times x tends to h tilde of 0 as n tends to infinity. This is some real number which gives 0 when multiplied by 0. We now know that h tilde of x is equal to 0 for every real x. In our study here, we have considered a non-zero x, but definitely if we put x equal to 0, then we also get 0. H of x is equal to h of beta of x for every x in R. H of x is equal to h of beta of x. Replace x on both sides by beta x. H of beta x is equal to h of beta squared x, and so on. Like above, we can use induction to show that h of x is equal to h of beta to the n times x for every positive integer n. We also have that function h is continuous at 0. We can take the limit of both sides as n tends to infinity. The left-hand side is h of x. The right-hand side, by an argument similar to here, is h of 0. H is g of x minus f of x. h0 is g of 0 minus f of 0. Function f is a constant times x squared plus a constant times x. F of 0 is equal to 0. In the problem statement, it is mentioned that g of 0 is equal to 1. So h of 0 is equal to 1. H of x is equal to 1 for every x. G of x, the required function, is f of x plus 1. This is the only function that satisfies the conditions mentioned in the problem statement.